Hi, and welcome to the section 9. This section is to be posted for the week starting November 2nd. And what we're going to do today is we're going to make this the last section that we're going to cover stuff in the Hector-Lean model. And so today what I'm going to be covering is I'm going to be covering unit cost functions, which is a very helpful way that you can work with cost functions in the Hector-Lean model. I'm going to think a little bit about the factor price and sensitivity theorem and also the factor price equalization theorem. And then I'll post an add-on where I revisit the Rubinsky theorem a little bit later. So what I first want to do is I want to consider a firm that's going to produce a good using labor and capital. Its production function is going to be fairly standard. It's going to be the standard Cobb Douglas form that we've seen many times before. And so in this case, there's a couple new things. There's going to be this term that we're going to have called kappa. So sorry, kappa is right here. And kappa is just going to be defined like so. So this is going to be kappa right here. So it's just going to be 1 over alpha raised to the alpha, and then 1 minus alpha raised to the 1 minus alpha. That's not super important for now, but we'll come back to it. It'll be useful in sort of our computation. Our production function has this term A here. So this stands for TFP, or total factor productivity. And then we have labor raised to the 1 minus alpha and capital raised to the alpha. And so L and K are just the quantities of labor and capital used in the production, used in the production of K units of the good. And then we denote here W and R as the wage and rental rate of capital faced by the firm. So if I want to hire labor, I have to do so at the wage W, and then if I want to hire capital, I have to do so at the wage R. Okay, so that's what we have so far. So problem 1, part 1, what we're going to think about is we're going to think about what are going to be the firm's optimality conditions. And so the first thing that we want to do is we want to just recall their production function. And so going back to section 1, part 4, where we learned about Cobb Douglas utility functions. Well, what did we say here? So we said that if with a Cobb Douglas utility function defined over consumption of 2 goods, where that looks like Q1 to the alpha and Q2, Q2 to the 1 minus alpha, then with such a utility function, the amount that we're going to spend on the consumption of good 1 is going to just be alpha. So I'm going to spend alpha % of my income on the consumption of good 1. And with such a production function, I'm going to spend the remaining 1 minus alpha on the consumption of good 2. Okay, so now we don't have a utility function, we have a production function. And so it's going to be a very similar format. Here, this 1 minus alpha suggests that I'm going to spend, so whatever revenue I produce, it needs to get paid out entirely to the factors of production that I use to produce my output. So this is what this is going to say is this 1 minus alpha means that I'm going to spend 1 minus alpha of my firm's revenue on hiring labor. And so 1 minus alpha times I, and so I is going to be the firm's revenue, is going to get spent on hiring labor. And so how much do I spend on hiring labor? Well, I spend it times the laborers that I hire times the wage, or this is the price to hire each worker. And so sometimes what we call W over L is, we can call this expenditures on labor, or equivalently, sometimes we also call this the wage bill. Okay, and so likewise, what's the amount that I'm going to spend on capital? Well, it's just going to be the remaining alpha of my revenue. So RK, this is the amount that I spend on capital, or the expenditures on capital is just going to be equal to alpha times what my firm's revenue here. Again, this is the price to hire capital. That's going to be R, and K, this is just the number of units of capital. Okay, and likewise, I, again, is firm's revenue here. So this, these are going to be our firm's optimality conditions. And just to write it out on the screen, perhaps with a little bit neater handwriting, the wage bill, as I've said, is going to be equal to W over L equals to 1 minus alpha times I, and then capital expenditures are just going to be given by RK times alpha, or RK equals alpha times I. Okay, so in parts 2 and 3, what we want to do is we want to express the firm's demand for labor as only a function of the variables W, R, Q, and the parameters alpha and A. So here we've written the firm's demand for labor and so if I just divide by W on both sides here, we've written the firm's demand for labor in terms of alpha, their revenue in W, and we've written the firm's demand for capital in terms of alpha, their revenue in R. But what this is asking is it's asking don't include as a function the firm's function of demand for labor and capital. Don't include their revenue in there. So we want to just only have L and K be a function of those variables and parameters right there. So the first step is just to recall that I have this. And then what am I going to do here? All I'm going to do is I'm going to divide W over L by R over K. So what's that going to give me? It's going to give me W over L over R over K gets divided by, on the right-hand side, 1 minus alpha I gets divided by alpha over I. And so these alphas cancel out, and we're left with this expression here. Now what I can do is I can just multiply, for instance, this equation, I can just multiply it by RK up here. So these RKs cancel out. I can divide by W on both sides. And so what I'm left with is this expression right here. If instead I want to solve for K by itself, then I just undo what I did right there. Instead, what I'm going to do is I'm just going to multiply by K on both sides. So I write a K here, and so that cancels out. And then I'm just going to multiply both sides by alpha over 1 minus alpha. So these cancel out here. And then I'm just left with WL over R times alpha over 1 minus alpha, which is this expression here. Okay, so that's the first step. Notice that L and K are still functions of each other, and so I need to do a few more steps. So in order to solve for L and K only as a function of these terms right here, then what I'm going to do is I'm going to need to use my production function. So let's just recall that Q is equal to kappa times A times L to the 1 minus alpha times K to the alpha. So what I'm going to do here is, suppose I wanted to solve for instance, L as a function of these parameters. Then what I do is I plug in K here, and then I just solve for L by itself, because notice that K here is just a function of L. So when I plug in for K here and solve for L, I should get L that's only a function of those parameters. So let's do that first. So again, as I said, what I'm going to start by is I'm going to start by plugging in K here. So the first line of this is just this. In the second line, I've plugged in for my expression for K. So this gives me kappa times A times L to the 1 minus alpha times this expression for K, all raised to the alpha. So that's alpha over 1 minus alpha W over R times L to the alpha. Okay. What I can do is I can just take out this exponent out here, just multiply it in here, and then make a few simplifications. So notice that this here is L1 minus alpha, and then this is L alpha. So if we add these two up, so L minus alpha times L to the alpha is just equal to alpha, because if we take and add these exponents together, we get that this is equal to L to the 1, so that's L. So, so we can combine these two terms, and they'll just become L here. Any more simplifications that we can make? Well, what we can do is the big simplification that we really want to make here is we want to recall that kappa is equal to 1 over alpha to the alpha times 1 minus alpha raised to the 1 minus alpha. So what we want to remember here is that kappa is equal to, sorry, and this is just kappa here. Kappa is equal to 1 alpha to the alpha times 1 minus alpha raised to the 1 minus alpha. So a couple of things. First, this alpha over alpha is on the bottom, and this alpha over alpha is on the top, so we can cancel those out. So that's good. And then what I want to recall is that I want to recall that I have basically alpha still here. But notice that 1 minus alpha all raised to the alpha is the same as 1 minus alpha to the negative alpha. So this expression now just becomes 1 minus alpha to the negative alpha. And so if this is in the denominator and this is in my numerator, then these negative alphas just cancel out. And so what I'm left with is I'm left with just 1 minus alpha. And so this whole term cancels out here. And now we're just left with a 1 over 1 minus alpha. Okay. So I don't see anything more that we can do. So we just, I'm going to skip this line here. I've just jumped down to here. So we bring down this 1 minus alpha. We bring down this A. We bring down this W over R to the alpha. And we bring down this L here. Okay. And then all I need to do is I need to write L by itself. So the way I can do that is I'm just going to multiply all of this by its inverse. And so I'm going to multiply this side by 1 minus alpha over, over A times R over W raised to the alpha. So all of this should cancel if I've done this right. And so then we'll get on this side 1 minus alpha over A times R over W raised to the alpha, which is this expression right here. And just to confirm, notice that we want to express labor as a function of W, R, Q, and the parameters alpha and A. And so that's exactly what we've done. So moving on, what we want to do is we want to do the same thing, but to solve for K instead. So instead, in my production function, I'm just going to plug in this expression that we obtained earlier for L and do the exact same steps. So again, I just plug in this expression for L here. That all gets raised to 1 minus alpha. We can notice that if I move this 1 minus alpha in here and raise all of these terms inside of the 1 minus alpha, then we can notice that we have k to the 1 minus alpha times k to that alpha, so those alpha terms cancel out, and we're just left with k. So that cancels, and so that's how we go from this line to the next. To go from this line to this line, actually I'm going to skip this. Let's go straight to the one below. What we can recall is, again, kappa is just equal to 1 over alpha to the alpha times 1 minus alpha raised to the 1 minus alpha. Okay, and so if we bring this term inside, this gives us 1 to the 1 minus alpha raised to the 1 minus alpha, so these cancel. And then what are we left with? We're left with, just to pull this term outside so we can just look at it a little bit more cleanly, we can just notice that we have 1 over alpha times 1 over alpha to the 1 minus alpha. And so these alphas are going to add up and cancel out. And so what we'll get is we'll get that this is all equal to 1 over alpha. So this 1 over alpha comes down here. These a's don't cancel with anything. This r over w is still raised to 1 minus alpha. And this k didn't cancel out with anything. So we're left with that. This is all still equal to q. So again, to get from this step to this step, all we do is we multiply both sides by alpha over a times w over r raised to the 1 minus alpha. All of this should cancel with this. And so what we're left with is alpha over a, w over r, minus 1 time, all raised to 1 minus alpha. And so that's exactly what we get here. So we've written k now as only a function of alpha, a, q, w, and r. Okay, so that's what the problem is. So now what we want to do is we want to express the cost of producing q units of output as a function of only the variables w, r, q, and the parameters alpha and a. So recall that I said that I defined the wage bill of the firm. This is just equivalently the expenditures of on labor. So the firm's labor expenditure. It's equal to W over L. And so what I'm going to do here is I'm just going to take this function that we had for L right here. So, and I'm just going to plug it in here for L. And so the only simplification that I can make here is that R over W raised to alpha is equivalent to writing R to the alpha times W minus alpha. And so you can notice that this here is W raised to the 1. And so if you add these exponents together, you just get a W to the 1 minus alpha. Okay, and we can do the same for RK. Again, recall that RK is then the firm's capital expenditure. And so again, what we do is this is RK. We take this here and we just plug it in for K here. Notice that this R over W raised to the 1 minus alpha is the same as writing W to the 1 minus alpha times R alpha minus 1. And so these 1's cancel out because we have a 1 here. This adds up with this 1 here to make 0. And so therefore we get R to the alpha, which is down here. The rest stays the same. Okay, so I'll show you why this will be important. And the reason is that the cost of just producing Q units of the good is, suppose we need L units of labor and K units of capital to produce K. And so then that cost of producing that, or sorry, we need L units of labor and K units of capital to produce that output Q. Sorry, I called that K. Okay, so if I need these amounts of labor and this amount of capital to produce Q, then recall that I have to hire those units of labor at a wage W, and I have to hire those units of capital at a wage R. And so this is going to be the cost of producing, the total cost of producing Q units of this good. So now what we're just going to do is we're just going to plug in for this function of R over K is only a function of the amount Q we want to produce, and then the wage rate of labor and capital. So we have that instead of writing things in terms of units of labor and capital we want to hire, we're just writing as a function of the quantity that we want to produce, which will then tell us instead how much labor and capital we need to hire. So if we just plug those in, what we get is we get this expression right here. Okay. And so I can make a couple simplifications. Note that this term here is the same across both this term and this term. And also I have that A is in both terms. So what I can do is I can just pull out W raised to the 1 minus alpha times R to the alpha over A. And then what does the term inside become? It's 1 minus alpha times Q plus alpha times Q. Okay. Or if I write this out even further, so I'm just going to write out this term even further. That gives me Q minus alpha times Q plus alpha times Q. So these terms cancel. So what I'm just left with is W times 1 minus alpha times R over alpha all over A times Q. And so this is just going to be my total cost for producing Q units at the prevailing wage rate W and the prevailing rental rate of capital R. Okay, so another thing that's useful to define is then just to define the unit cost function. So what is that? The unit cost function is just the cost of producing 1 unit. And so it's really helpful oftentimes to just work with the cost of producing 1 unit. So if we call this term right here just the cost of producing 1 unit, because that's just multiplied by Q. And so you can see that we can break up the cost of producing Q units into this cost, which is standard for producing 1 unit, times just however many units there are. Then we can notice that this part right here is just the cost of producing 1 unit times however many units we're producing. So this is just the unit cost function right here. And then this is the number of units we wish to produce. And so then if we define little c just as a function of W over R, that is defined to be, so that's what this triple equals sign means. It's just defined to be the cost of only producing 1 unit at a wage rate, W and R. Okay, so you'll see why this is useful, but it's helpful just to think about the cost of producing 1 unit as only a function of the prices of the inputs that we use in the production of that good. Okay, so that's been part 1. I'm going to break this up into different parts. The next part, we're going to talk a little bit about factor price insensitivity.